Hello and welcome to a new video. This is for Pre-Algebra. We're moving right along to lesson 20. We're using the Math UC curriculum and we're having a good time. This week's lesson is about similar polygons. So just some vocabulary real quick that you may or may not already know. A polygon is a two-dimensional shape made up of straight lines. Poly has roots that relate it to the idea of saying many, and gon somehow is related to sides. So like if you translate polygon into based on whatever language it comes from, it's many sides is kind of what you're saying. You may have seen poly as a prefix to other words, although it's not used a ton, but it is out there, and usually it means many. And you may be thinking, oh, there's some shapes that I know that end in gon, and so that's related. The polygons that are 5 sides and above all end in gon, and in fact, you could name a lot of polygons that you would probably never actually even see if you just kind of stick with our naming conventions that we use. So for instance, 5 sides is pentagon, 6 sides is hexagon, because penta means 5, hex means 6. Sept would be 7, like September. So septagon. Octagon is usually one we're familiar with because that's what stop signs are. But you could go on and on and on. And eventually, actually, instead of actually using like weird prefixes, we just say the number gon. So like a 12-sided figure, you could call a 12-gon. It's kind of weird, but also kind of awesome, in my personal opinion. Really, the main shape that you can think of that has a name that would not be a polygon is a circle. And really, any shape that has some sort of a non-straight line wouldn't be a polygon. So if you had like 3 sides that were straight, but then the 4th side is a curve, that's not a polygon. So not that it's not an important shape maybe, but it's just not a polygon. We name things in math that are similar like this, by the way, so that we can like make generalities about it. So there are things that we can say are true about all polygons that if we try to put circles and other shapes like that in, it wouldn't still be true. So what we're going to focus on today is when polygons are similar. So that word similar in math in particular has a special meaning. Like it's similar to the meaning that it is in general, in that like when you have 2 things that are similar, they might look the same, they might be close to the same, maybe I don't even know. Maybe your house is similar to the house next to you because they have kind of the same floor plan. Maybe your hair is similar to your sister's because you guys go to the same, hair stylist or, whatever. Similar means that they look kind of the same whenever we use it in the real world. Similar for math is a very specific situation where we have the same shape but different sizes. So it's not just enough that it's like, oh, those look kind of like they're the same. We actually would look and say, okay, these sides have a relationship. They are proportional to each other. And one way of thinking of it is that if you take the smaller shape and you multiply its sides by the same number, you can get a bigger shape, and those shapes would be similar. So this is going to build off of lesson 19, or I think it was lesson 19, where we had proportions that we were solving. And so one of the ways to solve each of these is to set up a proportion and solve either in our fancy way we do just by looking at the pattern or by cross multiplying. There's more than one way to set up most of these proportions, and so keep that in mind that I might set it up a way that's different than yours, but if you're able to get the same answer as me, then it's super likely that you set it up correctly. It also may be that on some of these you don't even need to set up the proportion because of looking for that relationship of the bigger shape is so many times what the smaller shape is. It may be that you can just figure that out. So there's kind of 2 ways that we can set up our proportions. We either group together the sides that are talking about the same thing, or we group up the figures that are talking about the same thing. So here's what I mean by that. On example 1 here with these rectangles, I could do 3 over x because those are the sides that correspond to each other, that go with each other, and then that would equal 11 over 33. That's one option. Or I could say, okay, I'm going to put the 3 and the 11 together and then put that equal to x over 33. Now, in each of these cases, there's actually 2 things that we're like putting together because in the first one, each fraction had to do with which side it was. So the 3 and the x are sides that go together. They're the shorter side of the rectangle. The 11 and the 33 were both the longer sides. But the top numbers had to be related to each other as well. So the fact that 3 and 11 are on top, that's because they're both from the same shape. X and 33 are both from the same shape. If you look at the other proportion I set up, it's really like the same thing, just kind of like twisted around a little bit. And so what I did there is I said, okay, let me put the things from the same shape in one fraction and the other shape in the other fraction. But the top numbers both had to be the talking about the shorter side. And the bottoms both had to be talking about the longer side. So there are wrong ways to set up proportions, but in each of these, there's at least 2 different ways that you could set them up that would be correct. And in this case, there's definitely one that looks easier to solve based on like us just figuring out the pattern and using that. That would be the second way, because if you look, you might be thinking, okay, I know how to get from 11 to 33, that's times 3, which means that to get from 3 to x, I also need to times 3. And this is also what I was meant by saying, if you look at this figure and can figure out, that this is times 3, then guess what? This also has to be times 3. Let me just use all different kinds of multiplication symbols here randomly. So in either of those cases, that means we get that our answer is 9. It's a little trickier if we had set it up this first way, because figure out how to get from 3 to 11, that's a fraction or decimal. Now, there is a cool thing you can do where if you notice 11 and 33 simplify into 1/3, then that actually also is a way to make this be easier. But you'd have to notice that and actually do that to get that to work. So I feel like I'm being a little wishy-washy, but if you're able to get x equals 9 as an answer by some way that seems like legitimate math and not just guessing, then you probably have a way that's correct. One of the things we need to do as we learn math is we kind of make assumptions and then test them, and if they're right, then it's like, okay, this is how math works. If they're wrong, we need to adjust our assumptions. So definitely take the time to do some problems the way you think they should be done, check your answers, and if it's not working out that you're getting the right answer, ask for help, look at the solutions, whatever you need to do to adjust what you think is going on so that it's correct. But this is definitely, I think, one of our ways that there's a lot of different ways that you can think of this. And I would say that there's not just one right way for us to think about this one. So each of these are going to be then kind of similar. So example 2 has triangles, write a proportion for each set of similar polygons and solve for the unknown side. So we can set this up a bunch of different ways, right? So I could do like 36 and 4 together, and then that would mean I would do 45 and x. But for whatever reason, like the way I keep doing that, it is not the way that is getting us something that's easy to figure out. So I think actually it would be easier just to look at this and say, okay, well, what does it take to get from 4 to 36? I would have to times that by 9. What does it take to get from x to 45? Then it also is times 9. What we'd actually have to do, though, is go backwards, right? Because x is smaller than 45. So we actually going to say, what times 9 is 45? The answer to that would be 5. So x equals 5. If you did get this proportion and wanted to see it through this way, we could cross multiply. We have kind of some big numbers here to do that with, though. And so you might decide to have a calculator handy to help you whenever there's really big numbers. Should we be able to do it without the calculator? Absolutely. Will we do it if we don't use the calculator? It's a little bit iffier, but this should be 5. So that's how that works. One of the things I like about similar polygons, and in particular similar triangles, is there's kind of a cool word problem that we can do with them. And I'm going to show you what that word problem looks like using these triangles on example 3. Instead of this just being a 6, an 8, a 60, and an x, let's instead imagine that this side of my triangle is a person. This person is 6 feet tall. That's a very nice height. So that person's 6 feet tall. And let's say they're outside, it's a bright sunny day, although I guess it's kind of afternoonish, because they look on the ground and they see that their shadow is on the ground. They happen to have a friend and a tape measure, so they're able to measure that their shadow is 8 feet long. Now, why would this be helpful information? Well, it turns out that if you were to measure shadows at the exact same time, so the sun is at the same angle as when you measure it for your own shadow, you could use this as similar triangles and find the height of something that you don't know the height of, and maybe it would be really hard to find the height of, which is why I think it's cool. So in this case, I'm imagining that we've got a building or something right here that we're curious how tall it is. It's casting a shadow. That's a terrible looking building, but it's casting a shadow of 60 feet. So we're able to measure that with our super long handy tape measure and our friend. So we're like, well, hey, how tall does that mean the building is? We can set up a proportion. We can say, 6 and 8 have to go together because they're part of the same triangle, and X and 60 have to go together. Make sure that you put like the shadows both on the bottom or both on the top. They have to be like on the same level. So since 8 and 60 are both the shadows, I put them on bottom. And then we can cross multiply or try to figure it out however we want to. So if I cross multiply, that'd be 8x equals 6 times 60, which is 360. So I'm going to divide both sides by 8 and get x equals, that goes in 4 times with 4 left over. So we put it into 40, which is 5. X equals 45. And since I made it into a problem, we'd put feet. So we're saying this building must be 45 feet tall because it's casting a 60-foot shadow at the same time that our 6-foot friend is casting an 8-foot shadow. I don't know. I've always liked that particular kind of word problem. And then there's other things that are related to this, like example 4 here has a word problem that this is not technically a polygon we're talking about, but we're talking about something that has a proportional relationship, so I thought it kind of fit. So if I have a model airplane that's 10 inches long, the box says that the scale for the model is 1 inches to 15 feet. How long would the actual airplane be? And on some of these, you may be like, I can come up with this without even writing anything down, and that's great. Part of that has to do with we're doing relatively simple problems with relatively simple numbers just because we're in pre-algebra and we don't want to make it too hard too fast. The thing that would make this more difficult would be them giving us extra information or just unpleasant numbers to work with. So our model airplane is 10 inches long, and we want to know how long the actual airplane is, and our scale is 1 inch for every 15 feet. So, right, that means that if this is times 10, then this also has to be times 10. So 15 times 10 is 150. So our actual airplane that we're modeling our model airplane after would be 150 feet. So that's kind of the gist of this lesson that we're doing with similar polygons. And in fact, the word problem part of that is actually a little bit extra just for funsies. Like you're getting your money's worth here, which if you're watching it on YouTube, you're not paying any money. You're just paying your time. So I guess that's cool. But anyway, thanks so much for watching. I hope you liked the video. I hope you like the video by pressing the thumbs up, and please subscribe if you haven't already. I'm sure you have, but just in case, if you're like on the line between subscribing and not, just go ahead and click subscribe because you know you want to. And I'll see you in the next video. Bye.